Can you view my screen?
Yes, sir.
Yeah, thanks to this notability which actually gets syncs with the devices, different devices. So I could use at home as well. All right. So today is 10th. Is there a problem? No? So if you have any question, please you can ask me now. Yeah. So one of the fundamental theorem what we did last time is f from AB to R differentiable x equal to C lies in AB is a point of maximum or minimum, then f prime C is 0, right? So let us see an interesting application of this one, which you already know. So Rolle's theorem. Did you study Rolle's theorem in the first year course?
Yes, sir.
Okay. So you see, these things are getting repeated. Um, so what is the statement of Rolle's theorem? You need a continuous function from closed interval AB to R, a continuous function, and differentiable on the open AB, assume FA equal to FB, then there exists a point C in AB open interval such that f prime C is 0. So the point is that if fa is equal to fb, then and f is a continuous function and differentiable on the open interval, then there will be a point of maximum or point of minimum. That's what you need to show. All right. So proof. So since f is f from AB to R is continuous, so f of the image will be, and again an interval. So let's say alpha comma beta, right? Now the point is, see, we have fa. Oh, sorry. So yeah, fa equal to fb. No, I have something right. So this is not the correct assumption. Fa and fb equal to zero, right?
You don't have to assume them to be equal to zero, I think, just for them to be equal.
Uh, that is true. Equal. Yeah, equality is good enough actually, but we'll come to that when it is not equal to zero. At this point, you just assume this to be equal to zero. Yeah, equality. Yeah, equality is just good enough. That will come. That will come from the next one, next corollary. But in this case, you just assume this fa equal to fb uh, to be just
Equal to zero. Okay.
equal to zero. So it means zero belongs to alpha comma beta, right? Now, if alpha equal to beta equal to zero, then f x is identically zero for all x in AB, right? That implies f prime x is also zero for all x in AB. All right?
Sir, I have a question.
Yes, sure.
So, for example, we say that, say, like x, the function is differentiable for once,
Hmm.
or x squared, the function is twice differentiable.
Yes.
I Doesn't this mean that any constant function, or the zero function, to be more exact, is not differentiable?
Zero function is not differentiable.
Like by definition, because we don't say x squared is infinitely differentiable, but at one time it falls to zero.
Of course, x square is infinitely differentiable.
But we often say like have a twice differentiable function or thrice differentiable function which falls to zero afterwards.
Yeah, the twice differentiable function, which is not thrice differentiable function, that is something you need to construct. But the
Okay, so
poly,
we will consider that zero and the like are all differentiable. I mean by
yeah,
definition.
constant functions are differentiable function,
Okay,
and then zero becomes differentiable, right? So constant functions are differentiable function. Go with the definition.
okay, sir. I just read somewhere that they considered like n degree polynomials to be n times differentiable, and I
No,
think
no,
it's point of
any
notation.
polynomial is infinitely differentiable. Okay, it after n times it the derivative becomes zero.
I just think it was a point of notation. I mean, some people talk like that, but I
No,
mean,
no,
logically it's
nobody
infinitely
says
differentiable.
that it is n times differentiable, not n plus one times differentiable. Nobody in the world will say that. All
Okay,
right.
thank you, sir.
Yeah. So suppose so one of them must not be zero. So this implies so if alpha and beta both are zero, then it has to be identically zero. So this implies one of alpha or beta must be non-zero, right? Suppose alpha is greater than zero. right? So alpha or beta, one of them. So suppose alpha beta greater than 0, you take alpha only. So that means there exist. So but then alpha is also there exist. So maximum attains by continuity, since maximum is attained by continuity. By continuity, uh, so so maximum attained, that is by continuity. Yeah, I should give a bracket here. Therefore, f of there will be a c such that f of c equal to, or maybe x naught, f of x naught equal to alpha. So should write it. There exists x naught maybe such that f of x naught equal to alpha. All right. Now, since alpha greater than 0, again by continuity, there exists uh, epsilon greater than 0 such that, or there exists one point y in AB such that f of y is greater than 0. Y is different from x naught, right? So y in AB, y is different from x naught. So this implies what happens, we have at A, this is at A and this is B, and the graph alpha is something like this. Can alpha be greater than 0? Actually, no. So I should write here beta. So I should put beta here. So f of A and f of B are 0, right? So that means beta can be either less than 0 or equal to 0. Oh, sorry, alpha can be either 0 or less than 0. So you can choose, suppose here beta greater than 0. So beta is greater than 0, that means it is the maximum attains, right? So beta is greater than 0, so at x naught this maximum attains. Yeah, what I'm saying is this is not needed. The maximum attains here, and this implies uh, so yeah, I should put c itself because we get derivative to be 0 there. This implies f of c equal to 0 by previous theorem. Yeah, any problem here? Any question?
Sir?
Yes,
But maximum also maximum can also be at the endpoints, right?
true. You are right, but at the endpoints it is zero, right? And since beta is greater than zero, so it must be inside AB, open interval AB.
Okay, sir.
All right.
Yes, under.
Any other question? Again, if alpha is, suppose beta cannot be less than zero. So suppose alpha is less than zero, alpha is strictly less than zero. Then what happens? Again, there exists D at AB such that f of D equal to alpha. This is by continuity. Hence, this is fd equal to alpha since alpha is the minimum. F prime d has to be 0 by previous theorem. All right. Yeah. So if both are 0, then we already have all the points will have this property. If one of them is non-zero, which is suppose beta was the maximum, so beta is greater than 0. Beta cannot be less than 0 because at A and B endpoints it is 0, so it would be greater or equal to 0. So suppose it is greater than 0, then you have a point of maximum where derivative is 0. And similarly, if alpha is less than 0, then you have a prime d equal to 0. All right. Any question here? Yeah. This actually proves the theorem. There is nothing else. So that is the other important theorem. What I said, this theorem is the main thing.
Sir?
Yes.
So what if my alpha is negative and beta is positive at the same time? Then how can we prove that there exists a point its
Yeah.
first
So
derivative zero?
here we did not put any condition here about alpha. Alpha can be negative also,
Oh, okay, okay. So
right?
then if
Then
alpha can be negative, then why did we take alpha less than zero as the second case then?
because there beta can be zero, right?
Oh, oh, okay,
That case
okay.
is left. So there is
Right.
a intersection between these two cases. Non-trivial
Yes,
inter
sir.
that can happen that alpha is less than zero and beta can be greater than zero. Then you can choose any of the cases.
Yes, sir, got it.
Maximum and minimum will attain inside. There will be actually 2 points in that case where the derivative is zero, right?
Yes, sir.
Yeah. So that is interesting. So this is a good observation. There can be 2 points, more points. The points is not unique. Note the point where the derivative vanishes may not be unique. Alpha less than the case alpha less than zero and beta greater than 0 gives us 2 points. Just 1 minute, I have to put it in charge. So I have to I'll be back in 1 minute. Yeah. Class. Yeah. Yeah. So there are some cases where you get more points. So this is one case, right? All right. So now if we change this FA, instead of FA equal to FB equal to 0, if we just so remark, if we have F but not FA is not equal to 0, then what happens? Right? So again, in this case also we will get a point C in AB such that F prime C is equal to 0. How? We define as how define such a function gx to be fx minus fa, right? Now ga is 0 equal to gb, all right? Now g is continuous on closed interval ab, right? And differentiable on open interval ab. Therefore g satisfies all the conditions of Rolle's theorem. Hence, there exists C belongs to open interval AB such that G prime C equal to 0 and G prime C is equal to F prime C. Hence, this is 0. Alright? Is this fine? So, taking non-zero is just just defining a new function, it works. So, taking 0 is quite general. Any question here? Yeah, next thing is, so again in this case also picture is something like this, something like this, and this is, and this is, let's say this is A, this is B. So at A and B they are equal, right? Then you have a point here, or this tangent is parallel to x-axis. Now the point is, suppose this is not the case. So if A is not equal to FB, then how can you say? Suppose if A is not equal to FB, then what can we say? Right? So this is interesting. First, let me put as another theorem here. Suppose F and G are two continuous functions on AB and differentiable on open interval AB. All right. So now then assume FA equal to GA and FB equal to GB. Then there exists a point C in AB such that A prime C is equal to G prime C. Is the proof clear of this one? Now I have taken two functions, and at A both are equal, and at B also both are equal.
So let us define another function h such that h is f minus g and
Right,
apply.
right. Apply Rolle's theorem. Right. So proof: define hx fx minus gx. Apply Rolle's theorem on h. This is the proof. You write the details. So that gives you this one. But this is important. This gives you an interesting stuff. So another theorem which is called mean value theorem, and this is quite useful. But this is nothing but the corollary of this, a corollary of Rolle's theorem. So theorem statement is, suppose let f from AB to R be a continuous function such that if is differentiable on open interval AB, then there exists point C in AB such that fb minus fa equal to b minus a prime c. All right. So let me just draw a picture before we go into, before going into writing the proof. So suppose we have like this function, and a is this here, and b is here. Right? It's so outside you don't care. Just have to look at here. Now this is the point a comma fa, and this is the point b comma fb. What is the line joining between these two? Right? What is this line? Can you tell me? Equation? Equation of this line?
So y minus fa by x minus a equals fb minus fa by b minus a.
Y minus
Fa
by
by x minus a
x minus a,
equals fb minus fa by b minus a.
fb minus fa by b minus a, right?
Yes.
Right. So write this equation as y equal to fa plus fb minus fa by b minus a times, shift a little bit, times x minus a, right? This is the equation. All right. Now we define a function. Now let's come to the proof. Define a function gx which is fa plus b minus fb minus fa by b minus a times x minus a. This one, right? Do you see it? Just in a flash, you will get what is the result. Yeah. So I have drawn this line, and this line satisfies this. So g of a is f of a, and g of b is f of b, right? Because it satisfies this. This is f of b. F of, all right. So therefore, you apply this theorem. Maybe I should call this as theorem 1, Ross theorem 2, and this one 3, 4. Now apply all the condition of theorem 1 is satisfied. All right. All the conditions are satisfied. What are the conditions? F equal to GA, FB equal to GB, and F for G continuous functions and differentiable. But this is an affine function, so it satisfies. It is differentiable, and F is also differentiable on one interval, and both are continuous. So all the conditions of theorem 3 is satisfied. Therefore, there exists a point C in open interval AB such that f prime c is equal to g prime c. But what is g prime c? G prime c is fb minus fa by b minus a. Therefore, fb minus fa equal to b minus a times f prime c. Is this clear?
Yes, sir.
Right? This is very simple. Just one theorem which we have done in the very beginning about maximum or minimum. That is all useful. That actually gives a lot of things. All right. So any question? Now homework will be, so this is exercise. Apply the above theorems to f prime g, f g, f by g, right? Suitably to get new things, right? So you apply this theorem f plus g, and suppose f plus g has a maximum at c. So what happens? Then f prime c is equal to minus g prime c, right? So you put assumption on this, and you apply the theorem on this kind of stuff, and see if we find new things. Yeah. Any other question? So this is a source of lot of exercises. So you find a different function, nice function, or maybe a not so nice function using exponential or others, and see what happens.
Sir, can you explain the Rules theorem again?
Yeah. So what is the problem here? Rolle's theorem. What are the assumptions? You have continuous functions on closed interval, differential function on open interval, and at the endpoints it is 0. Then there exists one point in open interval AB such that f prime c is 0, which means that the graph has tangent at c which is parallel to x-axis. And first thing is you follow this theorem. Yeah. So this theorem. Use this theorem. All right. Continuous function. Then compact set goes to compact set. Connected set goes to connected set. That implies that it should go to closed interval AB. Closed interval alpha beta. So that we applied here. Right? So we get an interval alpha beta. Now, if both of them are 0, 0 belongs to there because we have at the endpoints, we have the value is 0. So 0 must belong there. So if both of them is 0, both of them are 0, then you see that fx is identically 0 because minimum is also 0, my maximum is also 0. So f is identically 0. That implies derivative of 0 is always 0. So this implies alpha beta must be non-zero. 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 So this implies al So this one you can, so instead of actually write next to consider the case when one of alpha or beta is non-zero, So suppose beta is greater than zero, it cannot be, it can be equal to zero or greater equal to zero, greater than zero. So beta is greater than zero, then the maximum, beta is the maximum, right? So beta is the maximum here. So maximum is attained by continuity. So there exists a C such that Fc equal to beta. Now you apply the previous theorem, which means this theorem. There exists a point of maximum or minimum. Here you point of maximum is there. So f prime C equal to zero. So other cases where the minimum alpha is less than zero, right? Then there exists again by continuity, there exists a point D such that fd equal to alpha and D will belong in AB, open AB. So alpha, so D will be the point of minimum, therefore f prime D equal to zero, again by that theorem, previous theorem. All right, this actually proves Rolle's theorem. Yeah, any question? Is
Yeah,
it
that's
clear?
fine now.
All right. So maybe one more thing here. So
Sir,
not exactly here. Yes,
uh, can you explain like what do you mean by new things in the exercise?
new things. So new things is you instead of applying at one function, you apply on two functions, these theorems, and see here you will get some things, right, in terms of f plus g. For example, here in the very beginning, here in this case, suppose f plus g, f and g are differentiable, f plus g are also differentiable, right? And suppose c is a point of maximum of f plus g, then what happens? Derivative of f plus g is 0. So that means derivative of f prime, I mean f prime c is equal to minus g prime c, right? So that is the only thing, that part is new,
Okay, sir. Got it.
right? It's like that. So if you apply Rolle's theorem on f plus g, and then what happens? You need such some conditions that f of a plus b g of a is equal to 0, which means f of a equal to minus g of a. So if you find some those kind of conditions in some problem, some exercises, then you can immediately see that you have to apply f plus g. You have to apply Rolle's theorem on f plus g. That is what actually I gave this exercise to construct your nice new exercises out of it, out of these things. You'll get some expression which will look new once at the end. That's what I meant by new things. And this is next one is just example of differentiable function. So one is constants, two polynomials. Okay, so next time we'll see the power series are also differentiable function where it converges. Okay, so that will actually give us a lot of functions to work with. Okay, so do you have any question? Okay, if not, then we'll finish here today. I will see you on Friday.